to YMT114 Principles of Software Engineering. This is the second part of Chapter 5, System Modeling. So we will speak about the rest of the topics we didn't cover in the last part or the last session of the videos. Topics that we will cover in this session are structural models, class diagrams, generalization, behavioral models, data-driven modeling, event-driven modeling, and modeling-driven engineering. So let's just go through these quickly and give a focus on what's more important and things that need elaboration. First of all, structural models are actually built or made or created or invented for having a visual or having a visualized view or real illustration and figures about the organization of the system. What do we mean by the organization? How the components of the system are fitting together and how the system is made from these components and what kind of relationships do they have. So the components of the system actually do matter in this case. One more thing. For the structural models, we model the system in two cases or in two states. The first one in the static way. That means just the structure of the model. We don't care much about any dynamic behavior. And the second one is exactly we model the structure while the dynamic execution of the model is achieved. That means during the execution or based on some, or we show the organization of the system while the system is executing or processing some data or dealing with some events. So why do we need to have these structural models? In brief, we may use them as a base for discussion or maybe also for designing the system architecture. So while these two types of requirements are always presented while creating or while modeling the structure of a software system. Class diagrams. We studied this actually in algorithm and programming 1 and 2. We have it in 1 and 2, I guess, yes, while we had some idea about UML. In brief, we have this kind of category for representing instance of objects and objects themselves, where we represent the objects by a square, and they have their own title, and next to that another field for attributes or their characteristics, and then another field for having their actions or the methods that they apply. So we may have class diagrams to show the classes themselves or the objects themselves plus the associations with these objects, how they are connected to one another, what kind of relation do they have, and this is what we refer to by association in this sense. So this is exactly the idea. So what is this object that we are speaking about? So we say object of a class. In the basic or in the very essential sense, when we say an object, we are referring to actually a general type or a general kind of a system or of an entity. Think of this. Think of a student as a general description as a class, and you may categorize this student to different types. Maybe a primary school student, maybe a university student, maybe postgraduate student, and there are so many categories. But the general view of this object is what we call a student, and it applies to anything, human being, animal kingdom, whatever, birds, and so on. So we have this view as a general view, and then we see what kind of objects are connected to this general view, and then we discuss or check the relationship or the association, which is actually a link between the objects themselves describing some sort of relationship. So this is the idea. We may create object or class diagram throughout different stages of software development. It depends on exactly what you are looking for while designing. So if there is any stage that dictates a class diagram, it's a good idea to start with, and I will explain why. So one of the things, before I go further, one of the things that makes our job easier is using the concept of generalization, which we will discuss it in a few slides. So look at this. We may have a class of patient, and it's associated with patient record. And this is what we call one-to-one association. That means a patient may have one record, patient record. And maybe patient record may have just one patient. And this is not usually the case. For patient record may have so many patients or so many records of patients. So we may have different patients connected to the same patient record. We will discuss those later on. This is a good example. This is a very good example. This is a class, as I said earlier. This is a class, and this is another class, and they are associated to each other. And well, this is one-to-one. Now, it's not practically available. Actually, we may have patient record for so many patients. Okay. Now look at consultation or consultant. Well, we may have a consultant for many patients, so one-to-many. We may have a condition described for a patient, many-to-many, many patients to many conditions. We may have many consultations attended by many patients. We may refer as many patients as we want to a general practitioner. So we have general practitioner 1 who checks a number of or many, and so on. So I don't want to spend more time. This is a type of association that we have in common actually in class diagram, where when we design this kind of view of software in software development. I'm sorry. So the idea of the class actually is exactly like this, as I said earlier. A name or a title of a class is just the name of the class, and then the attributes of the class. And then after that, the functionalities or the actions taken or made or done by the class. So you may have different or as many attributes as the program or the class dictates or the object dictates. And usually these are reflected somewhere here. What does it mean? Look at the voice note, record notes. Look at the transcript, transcribe. Look at the prescription. For example, we have treatment prescribe. New, for example, all these things like creating new, maybe a consultation. So this is the idea. We have usually those are set to private attributes, and usually we keep those public if it is needed, unless it is needed to keep them private so that we can access to them from other classes. We explain about this in algorithm and programming, so we don't have to explain about it again. Generalization, we explain about generalization is exactly as taking one type of a whole entity and giving its characteristic as general, and then if we want to go specific, we go as the you can say problem, or as the situation dictates. So the idea is like this. Well, we can facilitate our view about things by creating general name: animals, cars, houses, students, classes, faculties, universities. So we can think of this, we can think of them as general of their type, and then we can go specific based on the categories of these. But for example, when we speak about animals, we can have cats, dogs, etc. Cars, you can specify whatever car you want. I don't want to have any commercial in my videos. House is the same, maybe just normal apartment or land house or whatever. So you may think about all these as categories of houses. Okay. So the general characteristics are all available for animals. Well, you may think about what kind of general attributes animals have, or maybe human beings. Well, maybe you can think about the way we talk. Human beings talk, for example. This is a general attribute. So this is the idea. As I said, you can think of many types under the same general category, and this is essential in object-oriented, especially programming. All right, so it is used for modeling. This is used for modeling. It actually helps a lot. Why? First of all, it helps in implementation. That means it helps in facilitating the implementation job for object-oriented, as I mentioned, like Java, C#, or whatever object-oriented programming that you may follow for your implementation. This is number one. Number two, well, if we are generalizing, we will have a higher level and a lower level, or what we call is a superclass and subclass, or subclasses. So what will happen is whatever we have in the superclass will be available for the lower classes or for the subclasses. So if you need to modify anything in the superclass, you don't have to go and modify for all lower classes. It will apply to them. That will shorten your way of modification if there is any. That's a good thing to do in programming. So look at this, the hierarchy. We may have a doctor, and this doctor is a general category. We may have a hospital doctor or general practitioner. So there may be other types. I'm not quite sure about the categories of doctors, but this is just an example. So a hospital doctor could be a consultant or a team doctor. Team doctor could be a trainee doctor or qualified doctor. So these are hierarchies. All of them are doctors. They have the same essential characteristics or attributes of doctors. However, they have their own special characteristics other than the general characteristics of doctors. That's what we call generalization. So we have a doctor. Any doctor has a name, a phone number, email, and then we may register this doctor or deregister or unregister this doctor in our record for some reason. Now imagine this doctor. We have hospital doctor and general practitioners. Well, for hospital doctors, they have their own staff identity and, well, department or pager or whatever it is about their own field. For the general practitioners, usually we don't have staff ID. They are not permanent. They just practice. And we may think about address or anything that specifies them. So we don't speak about staff ID and their department, yet we speak about other characteristics that describe them. Okay, aggregation. The idea of aggregation is like, okay, imagine we have a class that is composed of collection of other classes. Okay, and now think of this simple example. Think about department, like software engineering department, as an object, and this department has a collection of instructors. So we have different instructors teaching at the same department, also students studying at the same department. So we can consider students as an object, general type of an object, also instructors as a general type of an object. They are included under one department. So this is what we call aggregation, and we may have this kind of association a lot. It's a part of, referred to usually part of, and widely available in software modeling. Now look at patient record, for example. By the way, before I forget, so the general type, or the type that is composed of different other types of classes, or a bunch of other classes, is referred to by diamond. Then we have this association as a line. The association in any class diagram is referred to by just a line. Then we have different types of associations. For example, this one is aggregation. Aggregation means what? Patient record may have patient, which is actually an object by itself. Okay, or an instance of an object, it doesn't matter, but for the time being it's an object, and also for a consultation. So in the record we may have these two objects. So this is the general type that combines these two classes within it, or composed of these two. Maybe other classes are available in patient record. So this is the idea. We have this diamond, like initiated by or stuck to the class or to the square as a class, and then ended by just a straight line to the class, which is part of the bigger picture, or like the bigger class. Okay, behavioral models. When we think about the dynamic behavior of this system, like the system, while the system is executing, while the system is running, so what happens during the system running and after the system runs or responds to certain event or stimulus, what happens? Okay, so this is exactly what we refer to by behavioral model. So we model the system in its dynamic execution. While the system is executing, and right after its execution, so we see how the system actually responds. And responds to what? This is what we call events or stimulus or stimuli in general. So these stimuli could be actually of two types, two main types. Either data, that means some input data that makes the system to process it or to take an action or to execute this data, or events. The events could be a trigger, like for example on-off, maybe a mouse click, could be, or a keyboard stroke or something like that. These are events, not data to be processed. But they create some series of processes that also create or are part of the behavioral model of a system. Data-driven modeling. When we speak about data-driven modeling, we focus on data processing. Why? Because most of current models are actually built based on data. So we have some data to be processed in the model. And in this case, what we do, we consider the model as a series of states, or not series of states, sorry, that's for the events. We consider like data processed by series of sequences of actions. That means we just look for one part of action to be taken by certain processing unit or processing step, then another one, series of those. So what is the idea of data-driven modeling? Why do we need to even have it? And how it is actually modeled? We use usually either external force or event or external input to a system and see how the system end-to-end is running or processing. That means from the beginning of the input of the data until the end, how our system is running. And based on it, we can decide different things. Whether for example, think about the requirements. Well, whether this is the thing the stakeholders are requiring or not. It could clarify that. Look at this activity model for the insulin pump operation, for example. Think about this stage, blood sugar sensor, for example. We have a sensor here to get sensor value. So this is an action. Now, while we got the data, we can compute sugar level. We explained about this earlier, if you remember, in some previous sessions. Once the sugar level is computed, then we can go to another type of calculation, calculate insulin delivery, and so on, so on. So series of what? From the beginning, from the sensor where we start sensing the sugar of the blood until we pump the insulin from the reservoir. So series of actions taken on data until we get the final action taken by the whole system. You may think of sequence diagram as a good way also for representing this kind of you can say behavioral model or data-driven model. You can think of it as just one direction from left to right of the process. Think about an order processing. We have an officer, it could be a system or it could be a human being, where this officer fills in some order and then there is a validation. Once the validation is done, then we have an update. We save the system, maybe then order. These are the instance of objects that we have within our system, and these are actors. So the purchase officer and the supplier. They could be automated. I mean, these could be automated, not human beings, but still, they may be also human beings. But this is another way of representing how the behavior of the system while processing an order. So we just go from left to right without considering anything from right to left. We just go like a flow of a staircase from left to right like this. Event-driven modeling. This is a bit different from data-driven modeling. We focus here on event. So what we care about is not data being processed. We care about the events. And this is widely available in real-time systems. You may think about triggers that stimulate systems, and we consider them as stimuli. that make the system move from one state to another. So in this case, what we are referring to by a system is a series of states. And these states are finite states. And these states will move from one state to another based on a trigger. And this trigger is what we call event. And that's why we refer to it by event-driven. So the idea of this is like we need to have some stimuli or some stimulation that allows our system to move from one or have the transition from one state to another. So how do we have such a thing? As I said, we think of it as a finite state machine model where we have states and our system will move through these states based on the input or based on the trigger that we are providing. These triggers could be external or internal, and we will see we have some examples about those. They are widely available in our life. I will just give a very general example that most of us have at home. And usually the description of this kind of state machine or whatever is available in UML and widely used. And I will ask also in your first assignment to do this very soon, but not now, maybe within next week. Okay, now look at this state diagram of a microwave. This is extremely basic microwave, not detailed. Why? For just simplicity. Now I think this is the beginning, the start. When we have like a microwave at home, we see like there is a waiting, just displaying the time. And if you want to do anything, you set the power. Let's say we have the option to set the power for full or half. Or also we have the way to change it if we are changing our mind, to reset it to full or half after being set to full or half, change our mind, then setting the time for how long you want to cook or for how long you want to set in the microwave, whatever you have. Then after that, if the door is open, it will not start for safety reason. If the door is closed, then it will enable the microwave and start operating until the time is over or until you open the door, or until you cancel. Once the operation is done, then it gets back to the initial state, and this is the final state, what we have here. This is exactly the behavioral diagram, which is represented by a state diagram of moving from one state to another. Here we don't describe any data. Well, you may press, this is an input data, but we don't care about it. What we care about is the states. And as you see, we have descriptions of the name of the state and what the state does, and then also the kind of association between these states and their descriptions. This is what we usually do in software modeling for the behavioral model. Okay, this is not enough. Why? Well, this is extremely abstract, and if you want to get some details from it, you will not know, especially if you are not familiar of what this is. So we may need to have what we call state-based description, where we describe all the states in details. I don't want to read those, you can go through them, but you have all your states explained and what they are actually doing. And this will make us actually fed up writing all these states, especially if the system is quite complicated. And this will not be practical in software development. Usually software systems are quite complex, especially if they are developed for big companies or big organizations. In that case, we will just exhaust ourselves writing thousands of pages for descriptions of stimuli or whatever the stimulus and its description. And for that reason, what we do is we can have something we call superstate. The superstate is encapsulating all these states that we have in just one state, and we refer to it by as general behavior, general operational process. For example, operation, we can refer to all these states as operation. We can encapsulate them under operation. And what we care about is like disable or waiting, or for example, whatever the states that inside, we just keep it under one state. And in that case, we will master the complexity by just encapsulating all similar states together to lower the level of description. Like this is just a piece of you can say detail. Well, if you want to detail all of them, we will not have even enough time and effort to do that. Model-driven engineering, MDE, is actually an approach in software development. It's a type of software development where we don't actually write programs. We create models and transfer these models to programs. How do we do that? They claim, those who develop the model-driven engineering or come up with this idea, that we can create the models. So you just model, like class diagram, for example, and then based on them, we can create our own or automatically generate our codes from these models. Then in that case, well, we don't need to have an implementation team. That's not needed. So what we need to do is just create these models and then transfer the models or interpret these models or translate them to some codes. Well, this one is theoretically possible, but practically is it? So this is a question, and this argument about whether it is possible or not is still going on. Maybe one day, yes, but it's still extremely at an early stage, and we are not quite sure about its validity. What kind of advantages and disadvantages do we have from MDE? First of all, well, we can use the abstract level for creating systems. That means we will skip a lot of details from the system itself. And the second thing, we will generate codes automatically. That's much cheaper. Okay. And then we can adapt our systems to whatever platform that we are looking for. How about the disadvantages? Well, when we consider modeling in an abstract view, well, we may not exactly create the proper implementation of our own system. Abstract usually drops a lot of details, and these details may be extremely needed. One more thing, well, we will save some time, save some effort and time and cost from coding part or implementing part, but we will need to pay much for developing our own translators, because when you create a model in an abstract view, you need to interpret it. So you need a translator or an interpreter to convert it to codes, and that's not easy to do, plus it is extremely expensive. Okay? Expensive means time and effort. You need a labor or you need specialists to do that for you. Model-driven architecture, this is a predecessor of model-driven engineering. So MDA is the predecessor of MDE. The difference between them is exactly MDE is about all the steps in software development, all the stages or all the phases, but for MDA is specified for design and implementation. So we look for design and implementation, and we model them by just MDA. This is a bit focused. It's the subset actually of MDE. And we have some models to describe this in UML. There are some models available in UML to do the description of MDA for us. So the idea is like this. Well, we create, as I said, we create different levels of abstractions. So we have different levels of abstractions, and what we think about is platform independent model. Platform independent means what? We don't think about any platform that we specialize for some, you can say, running process or development process or whatever environment that fits the software. So we think about it this way, and then we see, well, can we generate the working program within such a scenario or not? There are, according to the recommendations of those who invented the model-driven architecture, object management group, it's those who designed or those who invented the model-driven architecture is actually the object management group. It's abbreviated to OMG. Oh my God, you can remember it this way. Okay, so this is the way it is abbreviated, OMG. So it's a very famous group in software development. They came up with this model-driven architecture. They recommend 3 types of model for MDA. The first one is the CIM, the computation independent model. We focus only on the domain models, what the domain dictates, maybe for security, for safety, for whatever it is. So we focus on abstraction exactly used for those. The second type is platform independent model. This is a very general, where we like have certain reference to implementation, for example, like things for we model the static view of the system, we model the behavior of any responding to external or internal events, and so on. The last one, this is a more focused view of the platform independent. We move to platform specific or PSM. So we transform those to a platform independent model. So this is a bit more specific. And this is exactly where we need to spend some time working on having an interpreter to move whatever we have here as a model to something specific that runs on specific platform. And I will give some examples. Now look at this. This is the MDA transformation. We have a computation independent model. This is the exact first one. Okay, and this one with some domain specific guidelines and maybe human intervention by some translator, we can go to platform independent model. Once we have a platform independent model with some translator and some platform specific patterns and rules, we can create the platform specific model. Once we have the platform specific model, we can translate it to executable code based on language specific patterns. So we can create different types of code based on different types of rules and patterns for the language. And this is possible theoretically, but practically it has a lot of problems. Okay. Look at this. This is an example. Imagine we have a platform independent model. So this is exactly here. So let's say we have this model. We can use the Java 2 Enterprise Edition translator or the .NET translator for creating two different types of programs. We can use a specific model for the J2EE to create Java code based on a Java code generator. And we can do the same to create the C# program. This is, as I said, theoretically is possible, but practically it takes a lot of time and effort and actually energy from the organization willing or wishing to do this. As I said, the adoption of MDA by itself is limited by a range of factors. The first one, we don't have the specialized tools to do this kind of transformation. These tools are not available. And the tools that are available, actually, they are limited to some organizations. They develop these tools for themselves. Well, if some organization or a big company is going to have or is going to adopt MDA, it will not develop these tools on its own because this is a very specialized job. Maybe it will hire another company specialized in this job to do it. How about if this company leaves business? What will happen? So if this company leaves business, the company that hired this company to develop these tools for it, then it will have a problem in future in the continuous maintenance or whatever needed for the update or following up with the modern technologies. This is a problem in the adoption of MDA. So as I said earlier, models are always used for discussion. They are a very good way to develop or create a good environment for discussion. But the abstract itself is a problem, especially when we are transferring this abstract view in the implementation process. Sometimes we get a problem with what? Now what we say is we are trying to skip the implementation because it takes time, maybe effort, maybe money, because we need some implementation team, some sort of engineers or some engineers who are specialized in implementation. Well, maybe implementation is not a big or major problem in many systems. So this is not the major concern in many systems. Usually in software systems, we have bigger concerns about security, about dependability, about integration, legacy of systems, testing. All these things are actually more important in complex systems than implementation itself. So these are actually reasons that limit the adoption of MDA, one of. And as I said, MDA by itself is, you can say, an idea, partially available, but not fully. Well, maybe in near future, some bright people will come up with better ideas of adopting MDA and better systems or tools to allow us to use MDA in our life. If it is successfully done, we would have a great modeling scenario that lets us or allows us to, you can say, in properly invest our time and effort to create software packages or applications with much less time and cost. So the some other reasons. Sometimes we may think about well, the platform independent. Well, in platform independent, as I said, if we want to create them, we need to have translators to translate them to platform specific. Is it easy to create that? Well, it is extremely expensive, and maybe it will outweigh the whole idea of adopting MDA. So we may think about also the competitor of all these processes, the Agile method. Agile method itself is extremely evolving now, and it's adopted by so many companies in order for them to save their time and effort and come up with a better way of software development. And actually, these are the main reasons that limit the adoption of MDA. Well, this is the end of our session. I hope you guys have enjoyed, and I hope you will learn from it. Until our next session or until our next chapter, have a good time. Goodbye.